Welcome to today's Manufacturing Engineering Media webinar. Our topic is achieving higher machine tool performance using pure serial interfaces. Hello, I'm Pat Wozniak, Senior Editor at ME Media. My beat includes covering developments in manufacturing software, CNC controls, and automation technology. Before the presentation begins, I'd like to provide some background on what we will be doing today. Our sponsor is HEIDENHAIN Corporation, a leading manufacturer of precision measurement and control equipment. HEIDENHAIN's measurement technology is utilized in high-precision motors, motion control, and machining systems worldwide. The company has more than 100 years of experience providing position feedback accuracy for precision measurement systems. You will be able to ask questions during the presentation using the Q&A box that will appear on the right side of the screen. Following the presentation, our presenter, Jimmy Rago, will answer your questions. If time runs out before we can get to all the questions, we'll make sure the answers are emailed to you. Portions of this webinar are pre-recorded. As often happens with viewing videos over the internet, the quality of the presentation may be affected by the type of internet connection you have, the amount of total bandwidth available to you, and the number of people accessing that bandwidth at the time. If you experience difficulty, please let us know via the Q&A app. Also, if you have questions about any other aspects of our webinars, please email me at pwozniak@sme.org. Jimmy Rago, our presenter, is the lead product specialist for rotary and drive encoders within the automation division of HEIDENHAIN Corporation based in Schaumburg, Illinois. An engineering graduate from the Rose Hulman Institute of Technology, he covers the HEIDENHAIN, Line and Lindy, and Renco product lines and is an expert on the use of analog and digital serial interface technologies in position feedback and motion control solutions. Now, here's Jimmy Rago.
Hi, everyone. I'd just like to thank Pat for the introduction, and we'll go ahead and get started. So today we're going to talk about how to achieve better machine tool performance using pure serial interfaces. So what you see here in front of you is the title slide. We have a HEIDENHAIN linear encoder, and coming out of the scanning head is a cable, and you see we have the cable blown up, and you see the data inverse, the clock inverse, the power, and the ground lines. And that's all you need if you're running a serial interface. Sometimes you even need less. So let's jump into it. So what are we covering today? Today we're going to talk about why would you want a pure serial interface. Some of the reasons would be you have reduced noise, higher position quality, smaller cables and connectors. You can connect to state-of-the-art machines. Then we're going to get into some real-life applications, talk a little bit about how this relates to functional safety. It's a big buzzword now. And then also we're going to talk about our answer to some of these questions, which would be our EnDat interface. So with that, you would have one interface for many different encoders, many applications, high position quality once again, diagnostic features, automatic machine setup, and then more information about functional safety. Moving on to the meat, here we go. So what we have here are two little pictures here. And what we're going to talk about is long wave error and short wave error. With long wave error, that is what we would quote, we say, plus or minus 5 micron for this 5-meter scale. And what we mean is that's the result of our work in making the graduation, so how good are those lines, how well are they spaced, and also errors due to mounting. So the long wave error is, all the coupling of mechanical and production and everything, all that error we say. And then we have short wave error, which is the error within one signal period. So if we look at this picture here, we have a dark gray area blurred out. And what we have in the bottom picture is we have two sine waves, say a 1 volt peak to peak, one sine wave and one cosine wave. And then we have above that the error within one signal period, position error. And what you see is that even inside that one signal period, you have this what we call short wave error. which comes from the interpolation. So you have noise, errors induced from your electronics, whatever you're using to interpolate, and also from electrical noise from other things in the area. Maybe you're running your signal wires next to some other machine that's generating a lot of electrical noise, power lines, all kinds of things. And what the shortwave error does actually is it takes those two sine waves you see at the bottom, and basically it just makes them fuzzy. Think of it that way, and we'll see that on the upcoming slide. So we see here, the sine wave again, say 1 volt peak to peak, and we see that, yes, there are some extra peaks and valleys on there. There's some fuzz in there, some noise. So this is noise is just from, we'll say, electronic interference from some other cables or machines running nearby. On the analog signal, you see that this fuzz is actually changing the look of the sine waves, the cosine waves. It's changing the position information. So it's affecting your accuracy. It's affecting where you want your machine to be. Your control is seeing these different peaks and valleys, and it's saying, oh, I'm supposed to be here. I'm supposed to be there. I'm supposed to be all over the place. So this actually does affect your workpiece. You'll see it in the workpiece. You'll feel it in the machine. The machine will heat up. The machine will vibrate. So you're going to increase wear and tear on the machine. And like I said, it's going to come out in the workpiece. Then if we look down at a purely serial digital signal, we see, okay, yeah, I see that fuzz on the on and off. There's still some noise in there. But the important thing to notice is that the on and off does not affect the position information. So you still have correct information because you're transferring it in a different format. You're kind of just transferring it in words. So you're getting the correct information to your control, and it's not being affected by the noise. So keep that in mind as we go through this presentation. What we have on this slide are two linear encoders. The top will be once again, 1 volt peak to peak analog encoder, and the bottom would be something purely digital from anyone really. So it's a digital encoder. And so if we look at the top again, we have our signals coming out. We have A and we have B. And then we have the signals are generated inside the scan head. They travel along this cable all the way to your downstream electronics. Could be 1 meter, 5 meter, 10 meter, who knows. And what we're seeing here is that it's being subjected to all the noise in the environment through the whole length of the cable. So that cable is absorbing all that different noise. And there's ways to deal with that via shielding, grounding, all kinds of tactics. But you still see, even on the downstream end, there's noise there. There's fuzz. Those signals are different than what they were when they started. If we move down to the digital encoder, what we have is the same sort of signal generation inside, but then those analog signals are transferred instead of meters to your downstream electronics to be manipulated. They're transferred only a few millimeters across the PC board inside the encoder. And then they're interpolated, digitized, turned into these data words, and they're sent across the cable, and they get to your electronics, and you have these discrete on-off points. So the control is just reading on-off, on-off, on-off. Okay, I know where I'm supposed to be, where I'm supposed to go. So it has all the correct position information across the entire cable run. Now we'll see it sort of in a third way. So what we have is on the top, we would have again your analog encoder, analog generator, and then on the bottom would be the serial or digital. So if we look at the yellow box with a 1 in it, that's where your signal is generated. That's about 1% of interpolation error. There's some noise in there too, maybe 3 to 5 millivolts of an offset. And we see our Lissajous pattern, which should be a perfect circle. But right now, it's oblong. It's misshapen. And then you're going to take that misshapen signal. You're going to send it down the length of your cable, which is shown in this green box in the middle. And then it's going to get to your subsequent electronics, which is this dark gray box. So once it hits here, your subsequent electronics, you see it's still got that same noise, same interpolation error. And then we take all this misinformation, we digitize it, and then we interpolate it. And so we're interpolating, we're taking this incorrect data, we're magnifying it and making those errors worse, and then giving that information to our control to tell our machine, here's where we want you to move, here's where you need to be. So like I said, you're going to feel that, you're going to see that, there's going to be heat, there's going to be noise. It's going to be bad. Now if we look at the bottom, we have a just a serial encoder, purely digital. So we have the same signal generated. It's got the 3 to 5, say, millivolt offset. It's got some noise on there. It's the same yellow box. But the difference is now we just keep it on the encoder. We digitize it, we interpolate, and then we transmit it. So you see after all of our digitizing and interpolation, we've conditioned the signal. We have we have what looks to be a perfect Lissajous pattern. We've reduced some of the noise, so it's actually 0.5% instead of 1%. And then if we move, we transmit it in a parallel or serial, in this case, big time talking about serial transfer. Gets to your downstream electronics, you receive it, and you get this very good position information. It's correct. It's what was generated at the encoder. And no matter the length of the cable, it's usually not going to be affected by the noise. So you have improved position information through the interpolation and conditioning of the encoder. Well, okay, that sounds great. Those pictures were fun. What does this look like, on something we're machining? So if we take a look at these 3 workpieces we have, that top surface you see, it's not parallel to the bottom surface. It's moving at an angle. So you have, say, an x-axis move and also a z-axis move. And so what you see here is we have, on the top picture on the left, 100 nanometer interpolation error. That's fairly low. That's a pretty good encoder. And you see that surface looks good. That's something you'd want to see. You'd love providing that to your customer or having that something to work on. And then we look down on the middle picture, 200 nanometer interpolation error. So that's just, middle of the road. And if you look at that surface, okay, there's some sort of a ripple or something going on there. I can start to see something, probably could feel it too. And then we go down to 500 nanometer interpolation error. And it's very apparent. This is something you would see, you would feel. And while it may not affect, whatever the pieces you're making may not affect its performance, it is unsightly. And, that makes a difference to people. If they see something wrong with their eyes, they wonder what else is going on. And what you're actually seeing, what you're seeing in those ripples, that is just a magnification of the signal period of the actual encoder that you're using for feedback. So that's what you're going to see, and it's going to affect your whole machine. And then just kind of moving on, we have more interpolation error stuff. If we look at that big green band right there, what we're looking at in this picture, in this graph, is motor current on the Y and time on the X. So we have motor current we have a device with encoder B with high interpolation error, so say 500 nanometers again. And we see the current that's going into the motor, and the spike, we have a band of, say, 35 or so amps, going up and down. Well, that's a lot of current going into your motor. So that's a lot of heat that's going to be generated. And also, that's a high magnitude of movements going on. So it's going to be noisy. There's going to be wear and tear and vibration. And then if we look at encoder A, this would be, say, the 100 nanometer interpolation error. And that band is much smaller, maybe 5 amps or so. So you can just see the difference in motor currents based simply on the interpolation. So you're getting that much more correct position information. You have that much more sound of a feedback loop, and you're not having as much issues with trying to position your motors. And all that excess current, well, this is what you're seeing right now. If you look at encoder B again, or system B with encoder B with a high interpolation error, you're seeing a lot of excess heat generated. A lot of oranges, a lot of reds, even bright yellows and almost whites. And this is just a linear motor. We're going to see another video of this same type of a linear motor moving around the stage. And then if we look at A with low interpolation error, yes, there's heat generation. You're putting electricity in there. There's resistance and things. It's going to get hot, but it's not as hot as something with such a low interpolation error. And that's going to work its way. That excess heat, it's got to go somewhere. It's going to go into your machine, maybe go through the machine into the workpiece, or it's just going to affect your motor performance. You can't get the best out of your motors, so you might even start seeing this in your electrical bill depending on what you got running. We move on and look at the heat generation again. This is sort of more of a practical example. We have just a ball screw moving a load here. So you see the dark blue is going to be about 25 centigrade, and the yellow will be 40. So that's a 15-degree temperature swing. And really what I'm showing you is, you have this heat generator in the motor, and I understand, yes, not all that heat from the motor is what's causing this ball screw to heat up. We have just mechanical losses which are being converted into heat. But once again, you have all that position noise and all this excess movement created from the poor interpolation that's going to be affecting your motor performance. So as I said, you're increasing vibration, you're increasing all these movements and jitter inside your machine, and that's going to increase the wear and tear, increase the heat generated in your machine. And those effects, that thermal expansion is going to have an effect on your machine. We'll take a look here at your workpiece. So if we see on the top two pictures, we have, those are just magnified versions of what you see in the middle. So the middle is the full piece. The top two pictures would just be the top ends. So on the left-hand side would be what we consider semi-closed loop. So that's just an encoder on the drive motor of the, say, the ball screw. And then on the left-hand side, you have a fully closed loop. So you have an encoder on the ball screw motor again, and then also you have a linear encoder attached directly to whatever axis. So they look the same right there from where we start. But then if we go down to the bottom at the end of the piece, if you look on the right, to me, in my naked eye, it looks pretty much the same as when it started. If we look on the left, there's a definite difference. So you can see that this hole is starting to work its way into the wall of whatever this piece may be, and it's not where it was where it started. It's not where it's supposed to be according to the model you made up, the drawings you have. So you're seeing effects of the thermal drift in your workpiece. Like I said, it's going to affect whatever it is you're putting out, whatever your end product is. The next slide, I'll click over soon, is going to be a video. And in that video, you're going to see the linear motor moving again. And so what's going to happen is you're going to actually hear some audible noise that's going on, and you're going to hear three distinct different types of noise. So in the first, say, 12 seconds, 0 to 12 seconds, it'll be low pitch, kind of a low hum. Then about 12 seconds to 22 seconds, it's going to be a really high frequency, and you're going to hear it's going to be a little louder. And then from, say, 23 to the end, it's, say, a 30-second movie, so the last 10 seconds, you're not really going to hear anything. And you'll notice that you'll see the difference in the frequency, response frequency, that we're going to be using for these different motor runs. And so what you're seeing is just like a coarse interpolation, a medium interpolation error, and real fine interpolation, so very low interpolation error. I'm going to go ahead and click, and you guys can listen. Okay, well, I hope you guys were able to hear that and kind of able to just see the difference. I mean, you really couldn't see anything with the naked eye, but you could definitely hear it with your ear. Another advantage of a pure serial interface, since you have less signals, no incrementals, no voltage sense lines, you can have smaller connectors. So you can have smaller connectors, smaller diameter cables. You're transmitting, you have less wires in those cables. So you have smaller, simpler connecting elements, lower assembly costs, and then simplified shielding for your cables, which is always great. We move on. Remember I brought up connecting to state-of-the-art machines. Well, what does he even mean? All right, what I mean is you have high resolution and high position quality because there's less influence of noise in your system. So you have reduction of heat losses. You have the improved performance just because you have such a high quality position. You have less shortwave error. Remember, we talked about that before. And then we have short position and readout cycle times. So what I'm saying is that serial communication, the electronics are improving, and we can improve the speed at which we transmit the signals. So now you can use these serial encoders in many real-time applications. So if you've got robots or maybe some sort of a printing application where you got to hit the laser at just the right moment, or shoot the ink out, or if you've got a packaging, maybe a dispensing application where you're dispensing, say, someone's prescription drugs or mixing chemicals and things like that, you have to have reliable, fast feedback. And you can do that with serial interfaces now. Also, you can store information on board the device. So we have the advantage of a lot more computing power inside these encoders. And so you can have electronic ID labels, meaning you could store information about your motor or maybe about the machine or things about service. You can store that on the encoder and then at some point pull it off the encoder so plug it in. Oh, this is XYZ motor. Here's all my important specs, control, that's it rolling. And also that's great for machine commissioning. It really shortens the process, takes a lot off your operators. Integrated sensor support. So now, like I said, encoders are getting smarter. So they can support different sorts of sensors. If you have temperature, you have vibration, and all these different signal processing things they can do so that you can transmit this information serially through the encoder wires instead of through excess sensor wires, like I said, just adding more and more to your cable costs. And then we think about it, kind of put all these advantages together, and then some of us have heard about the functional safety. So what do I mean? Well, functional safety is a big topic in Europe, and the waves are really coming across the ocean. Every day I talk to someone new about safety, and over in Asia, they're quick to follow suit when Europe does something like this. So what it did is it started with this directive, EN 954, and that was based on structure and architecture. By structure and architecture, I mean the mechanical structure of the machine, but also the architecture, the control architecture. And so there was some rules and regs there. And then about 2009, they thought they were going to change over, and they had to postpone it because of the crisis. And so what happened is actually people decided to take those 3 years to get ready, but it started again in 2012. There's a new directive, ISO 13849. What it does is it adds the probability of failure. So not only do you have to know, what ways your machine or instrument could fail, you have to be able to predict, how often will that happen. And the big thing about it is anything you're going to be selling something into Europe, eventually it's going to have to comply to this. I have this slide in here, so hopefully you guys will take a look at it later to really digest everything that's going on. I've got a lot of information here. But this is really useful because it kind of helps you break it down. We have EN 954, which is already expired, and it just talks about the principle is merely fault detection. And then we have types of standards. There's 3 types of standards. There would be A standard is very general, B standard is more specific, and C standard would be like application specific. So what they've done is they have these C standards, and in those standards they say, this is the level of safety you need in a printing application. This is the level of safety you need for a machining center or some sort of anything really, a lathe or whatever it is you're working on. You have these different standards that are available now. So we have EN 13849, which is talks about the machine and related parts and control systems. And then we also have EN 61508. And that talks about electrical systems. So that's more, I would say, the architecture. So you have to know, not only do you have all these mechanical things that could go wrong, but you have to determine, what are these fit rates, how can my encoders fail, how can all these different things fail, and probabilities. So it's all pretty complicated. I just wanted to give you guys this so you can think about it as we go on. So how does functional safety fit in with serial interface? Well, what it does is it pulls the responsibility more away from the machine manufacturer or control manufacturer and puts more of it on the encoder developers. And so what's happening is you have the improved transmission of signals, so reduced noise. You have a higher, better position quality. You have smaller cables and connectors, so less things to fail, less things to worry about in test. And you can connect to these state-of-the-art machines, which have all of these, machines getting smarter. They're able to detect all these failures. So you can reduce the probability of dangerous failures, which is a statistic you need to prove how safe your machine is. Then you can increase the detection of any of those failures, which improves the total reliability of your system, which is always good. Like I said, where are you going to use functional safety? What does this apply to? So it does depend on your industry. Some industries are not really concerned because the human interaction is not so great. But if we look at some of these pictures down here, what we're looking at is Isolde standing in front of a turning center, and she's operating this. Okay, there's some covers in the way, but she's eventually going to have to go in there and remove whatever piece that is. And if everything's not working right or something's wrong and she ends up getting something damaged in her hand or her arm, well, that's an issue. Those are safety concerns that are going to come up. Also, if you have assembly robots, handling robots, or if you have to do some teaching of a machine, there's many applications that fall under these harmonized standards, which goes back to the A, B, and C that we talked about before. And what do we do with this? What's our answer? Our answer here is EnDat. So EnDat is a bidirectional serial interface, which means you talk to the encoder, and the encoder will talk back to you. So it's kind of like dealing with your teenager, but it's a little more respectful. So you can communicate during operation. Errors can be read from the encoder. They can be cleared from the encoder. Data can be stored. So once again, those are the idea of the electronic ID labels, things like that. Like I said, it's back and forth. It's bidirectional, and it's on the fly. So we have EnDat, and we have it for all of our encoders. So you see all these encoders in this picture here, all these different form factors. These are all for different applications, and all these encoders are available with EnDat. Also, we have it in our linear encoders, our angle encoders. And we also have it in some incremental encoders. So you don't get the features of an absolute encoder, but you do get the advantages of, once again, a serial interface, even in an incremental. So many encoders, many applications. Handling, packaging robot, maybe you got to pick up a bunch of sausages in a machine, put them in a line of 6 so that it can be packaged, or you're printing ID cards, or you have an automation application such as maybe you have automated milking station where you're bringing cows in, and how does safety or EnDat or anything apply to automated milking? You got to make sure you're not pulling the udders off when you're removing those milking machines, or you have a rotary turnstile table. You got to make sure you're going at the right speeds and things like that. So there's a lot of things out there to think about. Once again, there's a lot of advantages I brought up about serial interfaces, and we have those same advantages with the EnDat interface. So we do have smaller, cheaper connectors, simplified cabling and shielding. We also have an increased power supply range. So instead of, say, 5 volts plus or minus 10%, you would have 3 to 14 volts as your power supply range. And then in your electronics, your components, you don't have to have 1 volt peak-to-peak receivers and things. So you have reduced cost for components and engineering thought that are going on your side. Also, we can process temperature information inside the encoder and transmit that via the EnDat interface. So once again, eliminating the need for you to transmit your temperature data through other cables. So you've seen this picture before, bringing it back to high position quality. And the important thing I want you to take away is that you have all this information and this position information that is brought up in the encoder, captured in the encoder, and that correct information is then transferred to your control. And also, signal interpolation, over 16,000 times we can interpolate a signal and not worry about speed losses because of the advantages of our parallel interpolation methods. That's just something to think about. And then here we have the features of diagnostics, which kind of plays into the safety aspect again, but also just general maintenance. We have alarms and warnings that are inside the encoder. Remember, all the machines are getting smarter, smarter, smarter. Well, so are the components. We have online diagnostics. We have what I call valuation numbers. I don't only call them that. We have an absolute track in the top, incremental track in the middle, post, and then we have position value information in the bottom. So basically, these are just like the health bars, the life signs of your absolute track. Is it green? Green means go, we're good. And then the position information at the bottom, what it is doing is comparing those two signals. So you kind of have a constant online way to look at, okay, is my encoder mounted correctly? Is it operating correctly? What are we doing? So this allows you to maintain the machine. You can see things as they happen. Also, if you notice these signals continue to degrade over time, you can think, well, Jerry the service guy is coming in next week. He's looking at this. maybe we just have them take a look at this encoder, see what's going on instead of waiting for it to fail. And then if I'm at, say, the Northwest Herald, and all of a sudden printing web stops and we have a big mess of paper, that's going to take days and days to clean up, not to mention, hundreds of thousands of dollars in time and equipment and everything. So scheduled maintenance is a good thing. Diagnostics again, so automatic setup, that electronic ID label I talked about. You plug the encoder in, the encoder knows what it is, all of its capabilities. It tells your drive, you control that. The machine manufacturers can also store information inside the in the encoder, as I said before, maybe when it was installed, how it was installed, offset angles, commutation angles, important things. Also the functional safety. So just to show you here again, we have the redundant position information inside one encoder transmitted across the cable. And then we have our EnDat master there. So basically we try to take care of a safety system for you in one small bundle. So then what does this mean for you? Just to bring everything full circle, we have cost savings for you. So we have reduced connectors, we have reduced engineering costs because of the lack of components needed in the control. We have functional safety, high reliability in the field, planning of maintenance, so you can see into the future, hopefully. What we dream of, right? And then implementation. So I won't lie to you. Sometimes it can get difficult, but it's not difficult in the sense of hard to deal with. It's just that it's like an onion. You can start peeling back all the layers and realize there's a lot here to end at. So we have right now a few different versions. We have the reduced version, which is we call small and easy, and we give you basically some sample codes. You just implement these sample routines. It takes about 7 steps to get an encoder running. And then if that's all you need is position information, well, you're good to go. You can do this, FPGA if you want. Also, you can do that a number of different ways. We have some interface boxes. You can use microcontrollers. Then we have the standard version. So it's a fully tested code block with a defined output interface. And what I mean is basically you get this IP. You pay for just a one-time upfront cost. No, not a license fee or anything, just a one-time upfront cost for the code. And also you can get some assigned hardware from the company Matset in Germany. We work with them. And you get, like I said, tested, predefined, you know it works, you plug it in, and if it's what you need, you go. You can also talk to them and have them help you work on a custom interface for you, or you can work on yourself. And then we have the full-blown version. We call it Functional Safety Master, and that has all the functional safety aspects of it. So there's a lot of extra things that go on or go into being a safe encoder, a lot of extra capabilities the encoder needs. You have different alarm bits, warning bits, comparisons that have to take place. And so we even have different ways of getting that. So we can send you sample codes, a lot of documentation to go along with this. EnDat demo tool software is available. As I said before, microcontroller solutions available on already established platforms. No licensing costs. Code size is relatively similar to other interface solutions on the market. And then one thing that's really important is that the hardware is really, really, really equivalent to the SSI or BIS implementation. So even if you do implement EnDat, you're not stuck because we're not making you go down an avenue that no one else has gone down before. So you're just traveling right along with anyone who would implement SSI or BIS. And then if you have room on an FPGA or something like that, you can definitely implement more than one interface. You can implement multiple registers in EnDat, or maybe EnDat and then SSI or things like that. So with that, I'd just like to thank you. Thank you very much for your time and attention. And then I'm going to hand it back over to Pat.
Hello, this is Pat Warsiak joining you again. We have received some questions, and it would be nice to get to all of them before our time is up. Jim, here's one. Can you explain to me once again what shortwave error is?
Yeah, okay. So if we look at what shortwave error is, just to maybe bring it back to the pictures I showed before. So that shortwave error is going to be what you put into the signal error. So you have your sine wave signal, and we all think of it as just a perfect sine wave, up and down, back to zero. And then the shortwave error is actually induced because of the electronics. So the electronics aren't perfect. They don't do the same thing every time. And you introduce noise in every signal period, and it might not be, you might not be able to compensate for it because it might be different every time because your electronics are responding differently each time that a signal is generated. So the long wave error is easy to compensate, and the short wave error is very difficult to compensate because, like I said, it's more a matter of how well can you interpolate, what methods are you using, and also how much noise is there in the system.
Jim, can you go into more detail about performance level and safety integrity level?
Yes, okay. So if we think about performance level is going to be more based on the mechanics of the machine. So I'll push this slide to you guys. So performance level is going to be like more fault detection and probability of error, and that's going to be you announce we have this many faults that are possible, and we can detect, say, we can detect 90% of the faults that our product may have. Okay, that's good. Well, that is associated with some number of probable failures or hazardous failures per hour. And then you have safety integrity level, which is really more along the lines of the electrical system. So you have, once again, all these ways, your electrical systems can fail, but also gets into architecture. So there's, multiple ways to achieve safety integrity levels. And what they are is basically, they're just ways to categorize. You have different bands of failures per hour you can have. So let's say you can have, in one level, it would be, you could have one hazardous failure in 1,000,000 hours, and the next one would be, the next level up would be 5 hazardous failures in 1,000,000 hours, something like that. So safety integrity level deals more with the electrical systems and safety-related systems. So how safe is it? How good is your safety system? And performance level has more to do with the machine parts and the system as a whole.
Jim, if the analog oblong signal can be cleaned up in the EnDat interpolator, why is it not cleaned up in the analog interpolator?
Well, the thing is, there's a couple reasons. So some of it, I guess you would want to say, is maybe political or just held on to from sort of older mentalities. Because in the past, what had happened is, we had EnDat with incremental signals. We still have that available, but the EnDat was in the past not fast enough for high-speed applications. And so even if you could clean up the signals, you try to use this EnDat and it's not fast enough, so you have to use your 1-volt peak-to-peak. And if you try to clean up the signals, what you're doing basically is you're hiding problems that are already there. So maybe your mounting's not as good as it should be, or maybe your quality of the graduation is not as good. So while you can, yes, electrically clean up those signals, it's HEIDENHAIN's belief that you should start with the best from the beginning. So you don't really want to have to go through and do these gain and amplitude changes to round out your signal, because then you're actually, when you're conditioning the signal, you can induce more noise that way when you're through those different methods. And like I said, then you're just hiding errors. So maybe you make it look pretty, but it's right on the edge of being really out of whack. So you do your test runs and set your machine up, and it looks great. And then once you get into real performance, things start heating up and there's some vibration. Your signal still looks great, but you're getting errors or poor performance, and you don't really know why, because the signal still looks awesome.
Jim, you said there was documentation available for people interested in EnDat. Where do you find it?
So that is available actually on the HEIDENHAIN website. So if you went to HEIDENHAIN.com, and then there's a documentation, actually there's a fundamentals section. So if you went to fundamentals and you clicked on that, you would bring you to EnDat, and we have a list of frequently asked questions. We have a section dedicated specifically to implementing EnDat and kind of walks you through what does it mean on just an ideology, concept-wise, what are you going to be doing, the physical layer, what do you need for hardware, and then coding, and then also just the block diagrams and things like that. Also, we have a new document we just added up there for implementation of safety as well. So that's all on the HEIDENHAIN.com website, and then you would go to documentation, actually it would be under fundamentals, and then you look for EnDat.
Jim, here's another one. Is there any signal contamination due to EMF?
Yeah, I mean, that can happen. So that is going to be more relative to, I would say, your application. So if you, and this can happen, I mean, if you get enough noise, you can throw off the serial signal because it's, you know, you're not necessarily running it at, for EnDat specifically, the signal levels aren't going to be, you know, thresholds of, say, 0 volts to 30 volts or things like that. So if you do have a high levels of noise or high amplitude, then it could throw off your signals, and it could definitely affect what's going on.
Jim, with regard to safety, is the U.S. market catching up to Europe? What's the status on that situation? So
I would say definitely a yes. You know, it all started in Europe, and from what I've heard, Asia is quick to follow. And there's been a lot of development over the past couple of years working with the different safety certification bodies. So we work with TÜV in Europe, but there are many different certification bodies, and everybody's gaining experience. Everybody's drawing new conclusions. And in America, it actually is catching on. You know, people are starting to be, I would say, definitely more proactive about it because there hasn't been any catastrophic things that have happened, which is good. Nobody wants it to happen, but once it happens, what you actually learn is, you know, where are the teeth? What sort of things can happen to you if you don't actually comply to all these different standards? So I would say yes, America is behind, but not by much. You know, it's just a matter of it wasn't mandated, it wasn't started here, but as people design things that are going to be sold in Europe, it's going to have to comply to these different safety standards. And I think it's just going to become a worldwide thing.
Well, unfortunately, our time is almost up. All unanswered questions will be passed along to Jimmy, and you can expect a reply via email. The entire webinar will be available for replay today at 7 p.m. Eastern Standard Time, and you can access it by using the same sign-in link you used today. As Jimmy proved with his presentation, serial interfaces play a vital role in getting the highest possible performance out of machining operations. To help keep you abreast of the latest in technology and techniques, SME and manufacturing engineering media have a host of ways by which you can keep in touch with the latest development in measurement technologies, including the January issue of Manufacturing Engineering will include a feature on measurement and inspection technology. In the February issue, we'll feature an article on measurement in aerospace, and the May issue will include a feature on measurement in medical manufacturing. Every issue of Manufacturing Engineering includes Quality Scan, which takes a look at topics of interest to measurement industry professionals. Thank you for joining us for this Manufacturing Engineering Media webinar. We hope you found it informative.